Good morning. Welcome back to the course. I am Dr. Amandeep Singh and I will take the plant simulation technomatics in this lecture. I like to talk about the distributions. Okay, I have just opened this milling process. The processing time is 1 minute. If I took uniform distribution you know that is also known as rectangular distribution. So, where we have just the start and stop, we have the minimum and the maximum value, and we know that the value would lie between these two values. We do not have much information. So, uniform distribution and triangular distribution and beta distribution, these are sometimes known as the lack of information or lack of knowledge distributions, because we do not have much past knowledge. We just have 2 or 3 or 5 or a very few number of observations, and we do not know what a distribution would it follow. We have just a minimum value and maximum value. We do not know what is happening in between. So, we just pick this rectangular distribution. If you remember, if you know, the rectangular distribution is just we have A value and B value, that is all. So, it is showing, if we have to put it in this way, stream, start and stop. So, I will just put start and stop. Let me say the minimum time is 2 minutes, okay, and the maximum time is 3 minutes. Okay. So, this is there. Now, I have just put start and stop, I have not put any stream. What is stream? If you know about random numbers, stream is the seed of the random numbers. So, when we talk about the simulation, what is simulation? Simulation, we are trying to imitate the reality, and what is representing the reality? What is representing our actual real objects or subjects? It is the random numbers which we are working on. So, where does our random number start from, or the specific? So, that is a stream. So, if for instance for there are two processes, I put the same stream here. Same stream means the random number will start from the same seed, and the successive random numbers would be same. For instance, if I put the seed value 2 here in one process and seed value 2 here in another process, so the 9th random number that is selected in this process and the 9th random number that is selected in this process, that would be same, 9th, 5th, because the seed is same, so the successive random numbers would be same. So, it is recommended to pick a random seed, not I would say random seed, but at least a different seed for different processes to have the good simulation process. So, if we do not put any stream value here, the software would pick a stream value by itself. Okay. So, I am not putting any stream value. So, I have just put uniform distribution. So, we know that the minimum time would be 2. Okay. Or let me say the time varies from 2 minutes 50 seconds to 3 minutes. We know that this is the minimum, this is maximum. Okay. First I will talk about triangle distribution. Triangle distribution is actually sum of two uniform distributions. Two uniform distributions are there. Two uniform distributions means just have the smallest value and the largest value. We do not know what would happen. But in triangle distribution, we have 3 values. We have the smallest value, we have the largest value, but we have the one value that is in between, but repeating for the maximum number of times. It is repeating for maximum number of times, that is the value is mode. What is mode? Okay, like mean, median, mode is there. Mean is the central value, mean is actually the average of the values, median is the central location value, mode is the value that is having maximum frequency. Okay. So, here we can put, if I pick the triangle distribution, it is showing stream C, A, B. Here A is the smallest value, B is the largest value, C is the mode value that is repeating for maximum number of times. When it is repeating, I am talking about the past data. In the past data, I have 5 or 6 observations. I know this is the minimum value, this is the maximum value, but there is one value which is trying to repeat maximum number of times. So, I can pick the triangle distribution. Based upon the past data, if I have a lot of observations in the past, I can pick normal distribution. Okay, if that fits good here. In normal distribution, it is asking for its parameters. Okay. The normal distribution, I would say normal distribution statistic, it is asking for stream, Now it is asking for mu and sigma. Mu is the mean or average, sigma is the standard deviation. Also it is calling for the lower bound and upper bound. Lower bound is the minimum value and the upper bound is the maximum value within which our distribution would lie. So we should have the knowledge of the distribution. As I said, the softwares are GIGO, garbage in, garbage out. So if you put the right distribution and you have the right numbers and be having the results of the simulation very close to the realistic conditions. So this is the work of a systems engineer to design it in a proper way. So if I change this time, you can see, okay, I do not apply, okay, because it is okay, it is showing, you know, if I do not put it in a proper way, this is stream mu sigma. I am showing the value of stream, it has just picked, I was showing the value that's 250 and 3. The value of mean was smaller than sigma. So that is why it said, okay, it is showing the negative value, it is not accepting, would not accept any other format than is required. So let me pick just constant time here, and it was, just to make you understand properly, it was 1 minute I will apply. So let me see if I run it for an 8-hour day and try to see the throughput, open, you try to see throughput, the throughut per day is 1167, okay, per hour is 48, okay, and the total throughput is 389 for an 8-hour day, for 8 hours, okay. Now if I change the processing times, open, if I change this processing time to, let me take 2 minutes, okay, and I change this processing time also to 2 minutes, in actual conditions we cannot change the processing time, the processing that it has to take, it would take. The milling, it has to, if it has to take 2 minutes, unless we change the tools, we change the machine, or we have the CNC machines, or we have the advanced machines, we cannot but work on more on the processing times. The processing times are fixed. Yes, in the plant simulation or in the manufacturing simulation here, we can think of working on the bottlenecks. The processing times are fixed. We can think of designing the layout in a way that the material flow is minimum and that the total time taken is minimum. Total time taken would be minimum, that means the total throughput would be the larger. Okay. So if I change this time, now I have increased the time to 2 minutes. Now I run the process and let me try to see the throughput here. You can see the throughput was larger before, so it has reduced now because the processing time is increased. Okay. It is 582 pieces per day, 194 pieces in a 8-hour day. Okay. So also we can have the setup time as well. For instance, a workpiece is to be manufactured, it will take 2 minutes for processing and 1 minute for setup. 1 minute for setup means, for instance, some milling is happening. If you have a milling process, what do? We just rotate the tool and remove the material. So it is removing the material from one workpiece. This is 2 minutes process. After 2 minutes, the machine stops, this workpiece is taken off and a new workpiece is brought in here, that is the raw one, and it will start process on this. Now this setup takes 1 minute here. So this is setup time. So this is setup time, this is processing time. If I induce setup time as well and apply, let us see what happens to my throughput now. Only in one line I have put some setup time. So the throughput is further reduced here. It was 197 pieces, so it is 194 pieces now. Okay, because the setup time is there now, another 1 minute is being taken. So total time taken in the milling process in the line 1 is 3 minutes now. Okay. So this was a brief introduction about the software, the major or the main objects that we can use. Now I will pick some examples. I have some examples for you to show you different layouts, and also the experiment manager will use, we will try to see the simulation that we can do in the software. So this is continuous material flow. I will select 2-lane track here. So traffic circle or segment table, traffic circle, pick and open the model. Okay. So this is the model, it is already running. So I will just run the model. You can see, okay, this is the trolley that can pick our material from. So this is source part, some processing is being done here. I can see what is the time of the processing here. the times is constant 1 minute. So, you can see it is happening. Okay, I will make it a little faster. Control panel, I will make it a little faster and then run. Okay, this trolley is running. Trolley is continuously running through the tracks. Okay, this is actually about 20 times faster. So, the processing is happening. Okay, it has happened for the 9 minutes. It is not stopping. So, what is the setting? So, there is no end time. So, it will continue for the infinite time. So, this is a kind of just a cell, an O cell. Okay. So, cancel, stop. So, segment table, open model. This is just showing a track, okay, how the track is built. So, let me pick user interface, okay, dynamic statistics, display panel or chart, open. So, in this model we can see the chart. What is setting? There is no end time. I will put the end time here 08 00 00, apply, okay. Let me try to run this model. So, it has run for 1 day. So, entity buffer is there, entity machine is there, this is similar to that. So, we can see the charts here, show chart. So, for only one machine it is showing the chart that okay, this is something unplanned, blue color is unplanned, then we have blocked, then we do not have any failure here, we have this waiting time for the about 37% of time it has been working. So, this is another example. Okay. Then tools and optimization. Okay, the important is experiment manager. I will just pick the buffer line optimization. Okay, this is line comparison open model. So, in this model what we have 3 lines. Okay. In this line there is throughput with no failure, there is throughput with failure, throughput with failure and buffers. So, there is there are buffers kept in between. If I enlarge it, this is buffer. Okay. This is another buffer. So, we have kept buffers in between. This is throughput. We need to see throughput with no failure. Another line is throughput. We have put some failure rates here. Okay, if I see the failures, it has 90% failure, 90% availability, it is 10% failure. In this case, there is no. In the first case, there is no failure. Okay, so let me try to run this model. Yes, this model has run for an 8-hour day. So, for with no failure, the PCs those were produced in a day were 477. With failure it is 347, but because failure is there, we have put the buffers in between that can store some of the material. So, it is about 417. So, also it is giving the percentage of the maximum throughput. Maximal throughput is 477. So, it is with failure we have 72%, and with failure and but with buffers we have 87% of the throughput of the maximal value. Okay. Then I can then in resources I can see broker and animation. So, shift calendar, worker. Okay, I will show you worker introduction. Okay, worker introduction model. So, this is the worker introduction model. So, in this case you can see the workers are just introduced into machine, and if we run this, okay, let me try to make it a little slower. Apply, now run. You can see the workers who are running it. So, I can see the number of workers are 2 here, and work pool is there, and the broker is there. Broker is trying to distribute the work to different workers. Okay. So, this is one of the example. Then okay, let me come to the major simulation thing, that is the experiment manager, tools and optimization experiment manager. Okay, this is one of the models where we have experiment manager. This experiment manager can show the simulation. Okay, if I run this model, or let me open this experiment manager first. It's at definition and evaluation. In definition, we have defined the output values. Output value of the workstation portion, start fail portion, it is working and failed. So what output do we need, and what inputs do we have? Input is the route delivery and mean time to repair. Okay. So if I run this model, so also I can define the experiments, that is for number of 100 number of parts, mean time to repair is this much, 5, 10, 15, then 5, 10, 15, this is for 100 parts, this is for 200 parts again. So these number of experiments would run if I run this experiment manager. Let me try to run. It has run for 8 hours. Okay. Now let me try to see experiment manager. Now I need to see the results. It has shown the results at the mean time to failure. If it is kept 5, so it is working for this much number of time. It is failed for this much number of time. So for the simulation of 100 parts, for the simulation of 100 parts again. Okay, this is for 200 parts. So it has taken 8 experiments. So I can see the report as well here. Okay, in the report it is telling that okay, there are number of experiments. In experiment 1 this happened, in experiment 2 this happened. Okay, this is the total failure, this is blocked time, then gray color is waiting time. Okay, all these things it is telling in the report. So in experiments, what has it taken? It has taken different random numbers. In experiment number 1, different random numbers are taken. Experiment number 2, different numbers are taken. What is experiment number 1? It was given here, the inputs that we gave, output values are here in this results. Experiment number 1 is 100 parts with mean time to failure as mean time to repair as 5 minutes. Experiment number 2 is 100 parts with mean time to repair as 10 minutes. Okay. So it is showing these experiments here. So we can have all different kinds of designs. Then rule, we haven't defined any rule based setting can also be done. This is, and like if we go to the detail of the simulation, these things are possible. So then okay, layout optimization, factory optimization. Factory layout is there. This is a factory, and we have made weird kind of connections here. So layout optimization can be done for where to keep what machine, then what would be the overall, what would the maximum throughput if we do that. So these models can be also, we can go through these things to find the optimization here. So another model I can pick here is from continuous material flow, tool and track, distance control. Okay, sensors are like if we need to, for instance, if we need to accelerate at some point, or we need to put brakes, or we need to put the okay, this is a light, and like we can do anything. Let me open this model. Okay, yes, this is an brake and accelerate model. So I have defined the method here, watch method. The method here is brake and accelerate. So if I try to run this model, okay, first let me see the event simulator. It is end time, okay, nothing. But just to see whether how it runs, you can see this is brake. After brake, it will just slow down. After accelerate, it will accelerate. This is speeding the speed. So at this point, brake would apply. It is accelerate now. The brake would apply. It will take a turn, accelerate. It will accelerate from this point. Okay. So this is a kind of an entity. This car here. Okay, we had just one kind of entity. This is another entity which is in the form of car. Okay, the name is Autosorter. So this was my sensor in continuous material flow. there are many models in this. Okay, so I'll just pick randomly something, some okay tools in optimization. I can pick experiment manager. Then I'll try to explain the experiment manager in more detail. I'll pick an example. So before that, let me pick something. Okay, transfer station. Okay, transfer station. I have a demonstration model here. Transfer station is, this is one cell. Okay, this is one cell. This O is one cell. This is another track here, two-way track. Okay, transfer station, it will just transfer the material from this cell to this track. Let me try to see the event simulator here. You can see the trolley or the container came here. Okay, the container is coming. Some machining is happening here. Some machining is happening at this parallel process. Okay, let us first see what are the process parameters here. This is a parallel process in which 2 into 4 processes are there. The times is again the default time 1 minute. Okay, so if from source it comes, then transfer station is there. We need not to connect transfer station. Transfer station, when we see the transfer station, so it will transfer, it will load, it will just load the process. It is connected to connect paths from the parallel process. We just need to put the name of the process, from which process it will pick the part from parallel process. Okay, then it will target or transfer the parts to line. Okay, so there is no connector required in between. We need to just mention the predecessor and the successor processes here. So sensor position is this one. So all these. So we can select load, unload, reload, move. So it is loading the parts. So all these attributes availability is 100%. We can select this. Okay, I wouldn't change anything, and let me try to run the simulation. So these containers are running. Some processing is happening here. It will taking 1 minute. So transfer station is then transferring the part to this container. So this container is just coming here, and this transfer station, it is connecting the part from this line 1 to the two-way track. Okay, if I see its properties, it is from line to the track. The name of this track is track only. Okay. So again from this there is another transfer station. Okay, there is source transporter as well. The source transporter, that is a source is there that is trying to transport material from some other frame or some other, using some other interface. It is trying to do that. So this is one of the objects that can be used. Okay. So this is just a transfer station. Okay. Now apply. Okay. So there are certain examples which are available for us to see how these things happen. So I'll just open the start page again and try to open this factory simulation that we had made once. So this is a factory simulation in which okay, let me close these examples. Okay, this is a factory simulation in which these processes are there. This is the process. If I put the names, this is the process, single process 1 and single process 2, single process 3, and the workers are working here. The times for the workers are put. The speed of the worker, which is defined by International Labour Organization, is 80 meters per second, and the times for the different machines are taken in a way that if it is an automated machine, so the time is actually noted while doing live experiments. So these live experiments were conducted. So this is single process. Okay, this is milling. This is single process. I haven't changed the name, but this is milling. This time is kept constant here, and this time is 1 minute and 10 seconds. Like that is about 70 seconds it takes to do the machining. Then setup time is about 26 seconds. So for this machine, these are actual times which are taken from the experiments. Live experiments are conducted. So these times for the second machine, these are the times, the about 2 minutes, that is 1 minute 55 seconds, 59 seconds for the processing, and for setup it takes 33 seconds. Okay. So these are all taken constant here. So this is run for an 8-hour day. Okay. And also an experiment manager, we have defined the output values. Output values is one is working and failed, and throughput of line 1 and throughput of line 2 we need to see. Like we can just see the throughput here, we can just see the throughput here in the previous way we did. So, we can just see the throughput of this run that we have done, it is 534 pieces per day, 178 pieces in an 8-hour day, 178. Okay. But if I run my simulation using my experiment manager, so when I define the experiments, I have defined 25 experiments here, okay, 25 experiments, and these processing time is taken actually 59 seconds, and this 59 seconds using random number table or using some random distribution, normal random distribution maybe. So, we have selected the random times, those random times are put here. 59 seconds was the mean, and this is the real random times, not 59, actually 70 seconds is the time, 70 seconds. So, 70 test 69, this is 69, 1 minute, 9 means 69, this is 70, 71. So, these are the random times. Okay, setup times are also random. So, these times are put in, times for milling, processing, milling setup, drilling, processing, drilling setup, grinding, processing, grinding setup. Then after grinding we have inspection. Okay. We have these machines here, go back, this is my milling machine, this is drilling, this is grinding, this is inspection 1, this is throughput through line 1. Okay. Then worker, certain pace of the worker, footpath, all those things are defined here. This is the model we made to, this is an hypothesized factory. Okay. So, define observations per experiment. So, there are 25 experiments which are conducted using the random numbers, and per experiments 50 replications would be taken. That is 50 times one experiment would repeat, and of these 50 times the box plot can be made for these 50 experiments. This is one observation. One observation means 50 experiments. The second observation is another 50 experiments. Okay. So, it is about a total number of experiments that happen is 25 into 50. So, 25 experiments are made, and 50 observations per experiment, those are given here. This is 50 observations per experiment. Then input variables are all these times, milling, drilling, grinding, processing and setup times, inspection 1. In the second line we have a modern manufacturing machine which is micro wire EDM, electric discharge machining. Okay. So, this is a modern manufacturing machine. So, in this case also the time is put to these 3 machines, inspection 2 is there. So, there are 2 lines which you can see, the 2 flow lines. First flow line is the conventional machines, milling, drilling, grinding. Second flow line is our modern manufacturing source, micro wire EDM, then inspection and train. So, we can see the both throughputs used after conducting these experiments. So, output values are all defined, we need to see throughput 1, throughput 2, and also we need to see the working and the failed percentages. Okay. So, let us start the simulation. So, observation, current experiment is 1, if you see a third experiment is running, fourth is running now, fifth is running, sixth experiment 50 observation, for each experiment 50 observation, for all the 25 experiments 50 observation will run. Okay. So, you can see the time 8 hours, 8 hours, 8 hours, it is running the multiple runs here. Okay. This is how the simulation is conducted using experiment manager. This is the exact, if I use the word simulation. So, it has generated a report. Total running time for the simulation is 36 seconds, 25 to 50 is 1250. It has run 1250 experiments in 36 seconds. Okay. So, this is my report. So, let me take it here, I would not close it. This is my report, it is telling okay, this is the simulation, this is the final picture that we have getting here, this is simulation. Experiment 1, if you would like to see, it has shown that okay, single process 1, station 1 and single process 1. It is showing that these are the times for which it is working, this is the time for which it is blocked, this is showing all these things. Experiment number 2, okay, all these things it is showing. So, it is showing, let me try to see the statistics here. So, mean value, standard deviation, minimum and maximum for experiment 1. okay, for all the experiments. So, this is the P and T test, we do not move to that. These are the tests, those are conducted, and this is the chart for that, not chart, this is a table for that. This is the failed time, working time, and also it will show the throughput, because we asked for the throughput. So, this is the throughput for the 50 observations in experiment number 1. Experiment number 1 means 50 observations. There are 25 experiments, for each experiment 50 observations. So, experiment number 1 has 50 observations. These 50 observations have this mean 177.4. Okay. These 50 observations have this standard deviation. It has this minimum value and this maximum value, left and right bound is given. So, for all these 25 experiments it is taken, the overall mean would be also one throughput, that we also see. Okay, for throughput of line 1 and throughput of line 2 we can also see here. Okay. These are also again for 50 observation, 25 experiments. So, let me try to see. Okay, this is the model, this is overview, this is values of experiments. Let me try to see the plots of these. So, these are the output values of interest. So, if you see this is each experiment and 50 observations are given. This is for the throughput 2. You can see now we have a box plot here. So, now what does this do? This, for instance, this is my experiment number 5, this is my experiment number 5, this line. In experiment number 5 there are 50 observation and this is box plot, this is my median, and you can say there is a whisker and the third quartile is quite lower, and we do not have the first quartile is kind of coinciding with my quartile 2. Okay. So, the upper whisker is very smaller. So, it is showing the box plot for each of the experiments. Okay. We can see the variation. So, you know, this is a very small variation here in experiment number 11. In experiment number 16 you can see again there is a big variation on the lower side. So, you can also see the overall variability is very high, overall variability is very high. Why it is there? Because the micro EDM, or this is actually the behavior, or you could say, yeah, behavior of the process only. Micro EDM process, we do not know the kind of experiments which we did not know that what time would it take. Sometime it took maybe 50, it was actually about in 100, it was 600 seconds, it took 10 minutes, sometime it took 15 minutes, sometime it took 20 minutes, sometime it took like gate variability was there in the overall process. That is why this big variability is there, number 1. Number 2 is the number of the throughput is very small. Actually, the final throughput that is obtained, the average throughput was 14 pieces. Throughput is very small. So, with this small throughput is showing very high variation, like in a day we can even, you know, we can see that we even have about 9 pieces in a day here. Okay. We have about 15 pieces in a day here. So, the total throughput is very small. So, that is why this much high variability is there. So, let me try to see this for throughput line 1. So, this I have obtained the chart for the throughput of line 1. You can say the throughput for line, the variability is less. Okay. There are two reasons for this. Number 1, the processing times were in control, because the machines were CNC machines when we conducted the live experiments. However, the processing time for the inspection was a little variable, because inspection was done manually. So, but overall, because there were 3 automated machines, so the variability is lesser than that we observed in our line 2. Okay. This is first reason. Second reason is this number, the throughput value is 178, the overall average is 178, which is a big number, and bigger number than that very small number 14. So, the throughput variability is lesser. However, in individual processes, because the simulation is trying to imitate the realistic situation. So, in realistic situation we can have the outliers, we can sometimes have the very long time or very lesser time than it should be normal. So, this, for instance, in experiment number 5 you can see again the whisker is falling down. It all depends upon the random numbers, and if I tell you the times were kept constant, but the seeds were all different. So, depending upon different seeds for these different experiments, and the observations were also very different, these different box plots are obtained. Okay. So, we can infer that okay, the variability is lesser in this, and number of workers we can keep varying the number of workers in this experiment. The number of workers those were employed were 4, 1, 2, 3 workers in line 1 and 1 worker in line 2. We can also think of employing 5 workers, that is 4 workers in line 1, 1 here, second here, third here which is not yet employed, and fourth here, and fifth one here. Then we can see okay, if we employ another worker, we can do cost analysis as well. If we employ another worker, what is the wage of that worker and what is the overall throughput? What is the increase in the throughput? If the increase in the throughput is lesser than, like the profit that we obtained from the increased throughput by employing the fourth worker is lesser than the wage that has to be paid to the worker, so we can just take off the decision, we can just deny this decision. So, the certain experiments that we can do, certain simulations that we can do. I think I should stop here. We have discussed enough about the Technomatic software for an amateur. This is a good start, like you have an introduction to how the softwares work, and how is simulation conducted in the softwares, and what are various kinds of layouts, and we can even optimize the layouts using these softwares. And there are certain, as I have told you, there is a great capability of this specific software, but yes, we can keep on using this. We can try to simulate a factory, we can make a big factory, and this is just a manufacturing processes, manufacturing systems. We can also think of taking, after this manufacturing system this is developed, these systems or the actually report that we have got, we can take that report to team center to finally support when actually things happen. So, we can just put okay, this is the schedule or the plan, these are things which are actually happen. So, what is the variation of the actual things which are happening in first few runs when we actually run this kind of setup. So, we can test those as well using these software tools. So, I like to stop here, and thank you for being in the course. So, we will meet next time. Thank you.